Arden Labs, specializing in high-performance software consulting, training, staffing, and development. Module 13, Benchmarking. You are now watching Lesson 13.2, Validate Benchmarking.
I can't tell you how many times a benchmark has lied to me. It's happened to me so many times that I almost don't trust any benchmark anymore. And it's so important that you validate your results and that you have some reasonable expectation for things, because if a benchmark is lying to you and you take it at face value, then you're going to be making really bad engineering decisions. And I want to show you an example of this. So I read a blog post a long time ago where the author was talking about merge sort. And merge sort is a really bad algorithm for Go unless you really get complex, because the idea of merge sort is you take a list, you cut it in half, 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 you keep cutting it in half, you do some sorting, and you merge these lists back together. So it's really allocation hell in Go. We're going to be really thrashing the heap when we do merge sort in Go. But this author wrote merge sort and decided to run merge sort using one Go routine, right? So it ran sequentially. Then decided to throw a Go routine at every split in the list. So consider that maybe unlimited number of Go routines. And then decided to leverage only the number of Go routines that we had hardware threads for, right? Or logical processors. So on my machine, that would be 8 Go routines. And they ran the tests. And what the tests discovered was that when it came to an algorithm like merge sort, running the sort sequentially with one Go routine ended up being the best. Now, that result was really bothering me, because really, when I ran with 8 Go routines, right, if you ran with the number of CPUs, that should always still be beating sequential, because we can at least do some of that work in parallel efficiently. It's CPU bound at the end of the day. So I didn't like it. So I went ahead and I wrote the merge sort from the author, and I added my own benchmark functions. So without having to look at the merge sort implementation, it's not important, we could look at this benchmark. So on line 18, I have an init function, and we're going to put 1,000,000 numbers into that collection on line 15. Once we add all those numbers to the collection, we've got 3 benchmarks. We have single, which is going to use one Go routine sequentially from beginning to end. We have unlimited, which again, every time we split the list in half, we're going to throw a Go routine at each half. So we'll have an unlimited number of Go routines, technically, right? Say for that 1,000,000. We're just going to throw as many Go routines as there are lists to sort. And then we do num CPU there on line 36. And that's going to say, well, if you only have 8 Go routines, then don't split the list in more than 8 parts. So we eventually only split to like 8 parts, and then we do all that sorting there. Okay, so we want to see what the results are of this test. And this is exactly the code I wrote and exactly the tests that I did to validate the blog post. So here we are. So we're going to do our Go test. We're going to say run, none of those, any test functions you might find. Run all the benchmarks. And I'm not going to look at memory because it's going to be crazy. Right now we're just looking at CPU performance. So here's the single Go routine merging this list of 1,000,000 integers sequentially. And what it gets is, let's get rid of the first 6 numbers here. All right, so that's 94 milliseconds it took to do it sequentially. You could see how much longer the unlimited was, right? I mean, we're talking seconds now. And then what we have is 114 milliseconds there, right, to do num CPU. In other words, these are the same results, basically, that the author had published in that blog post, that when it came to merge sort, using a single Go routine was faster even than running 8 Go routines in parallel. This still bothered me, right? The author saw this result and walked away and made that engineering decision. But in my brain, I still said that there's no way that num CPU can be slower than single. And after about a half an hour of beating my head and looking at code and just really truly believing that these results could not be valid, I ended up doing the following. I decided to run numCPU by itself. And when I did that, look at the results. Suddenly, numCPU was running faster than a single go-routine. Finally, the expectation that I had was being seen on the results. Now you might be asking, whoa, what's happening here? What's happening here is that when I ran all of the benchmarks together, I was violating a major rule of thumb, which was that your machine must be idle. You see, the test for unlimited produced so many go-routines and so much chaos that all of that hadn't been cleared out yet by the time the numCPU benchmark ran. And therefore, the cleanup from the last benchmark was affecting the performance for the last one. Once I let my machine go idle and just ran numCPU by itself, everything started to be more accurate. Now, this doesn't mean that you always have to run every benchmark in isolation. But if you know you have a benchmark like unlimited that's going to put a lot of stress on the machine, you absolutely don't want to run that in conjunction with other benchmarks. So for me, this is that classic example where you have to have some expectation. You have to validate the results. If the results don't seem right, either your assumptions are wrong, which is okay, let's fix them, or there's something wrong with the code, or in this case, the machine is an idle, there's something wrong with how we're running it or where we're running those benchmarks. So please, always validate your benchmarks.